Welcome, everyone. We have seen last time that special relativity arises, not surprisingly, as a special case from general relativity. And in particular, we have discussed the notion of time dilation. We have looked at the twin paradox. And I've also said that there are a few things that are maybe more general if we look at the twin paradox in the context of curved space-time. But one thing we haven't discussed is length contraction. And I got a bunch of questions from some of you about whether the length contraction that you may have seen, or that those who have asked have seen probably in special relativity, whether that and how, if yes, translates to general relativity. And this is actually a very good question, what length contraction means in this more general context. And I would like to spend the first 5 or 10 minutes explaining that. So let us briefly remember that last time we considered, as usual, our manifold of space-time, so 4-dimensional space-time manifold. And remember, at the very beginning, we defined that the manifold is essentially a set of events. And of course, you know that, but it's always useful and maybe necessary to keep in mind and to emphasize that an event is really something in space-time. In the set, of course, I mean, this is now recursive. What I said space-time is defined as the set of points. I think I said I used that as a definition of space-time. But if you think now intuitively of events, this is something that has a time and a location. So you would not only give space coordinates, you would only say here, but you would say here now, for example. That's an event. Now, if you measure distances between events, then these are, of course, necessarily distances between objects that have both a time and a space component. So it's not fully clear whether this distance should now be regarded intuitively more as a time or more as a space. But I gave you essentially an instruction of how to map out space-time. I said we do it using clocks. So in this particular example that I've drawn here, we would take a clock at this event started. So this is the event where I press a button at the clock, and then I can move around with the clock. And of course, as I move around in space, I also move around in a way in time. So at some point I press the button again of the clock, and that's another event. That's an event that is certainly at a different point in space-time. And now the clock, what it shows, the difference between the starting and stopping time, is what we call here the length of the curve or the distance. So a priori, the fundamental distance that we introduced is something connected to the intuitive notion of time and not to spatial distance. And that's why it was quite natural, essentially, to talk about things like time dilation, because what I also now again said is that, of course, this experiment depends on the path we take. And if I take a different path, and let me draw maybe an extreme one where I would just move much more nervously around a more or less uniform movement, that would be a path which actually has a smaller length in terms of the metric we introduced. That's essentially a consequence of what we have done last time and calculated in the case of the twin paradox. The twin who accelerates away and comes back will see less time passing than the person staying at rest on Earth. And this is now more generally expressed by the statement that a geodesic observer has the maximum time passing. So if you assume in this picture that the orange one would be a geodesic, then that's the clock that measures the largest amount of time passing. And the clock that made the green trajectory will essentially show a smaller time. And a geodesic is essentially defined by the maximum distance. So a geodesic, and we know that this is equivalent to a straight line in our affine connection language, is actually in GR the trajectory or the world line with where the longest, where you have essentially, if you are yourself traveling, the longest lifetime or the longest time experience, or also the clock shows the largest time. So by the way, I forgot to mention that, but it's actually not obvious that all clocks should behave in the same way. So in these postulates that I mentioned last time, in particular in the second postulate, I just talked about the clock, and the postulate kind of implies that this must be the same for all clocks, because otherwise I couldn't really connect the clock to a length if it depended on the clock, because the length of a curve doesn't involve information about the nature of the clock. So a clock can be anything, including a biological clock, or let's say the time we experience as passing, that's also in a sense a clock. And so all processes of that, of all time-dependent processes count as a clock. Anyway, so what I wanted to say is that for time, this was quite a natural statement. But what about length contraction? So first we have to remember that, and that was also a question that was asked last time, that even in this case of time dilation, the solution usually of the geodesic, for example, is not unique. So it could be that in a complicated space-time where you have, for example, a black hole, that there's a geodesic, with a world line passing on one side of the black hole and another geodesic passing on the other side of the black hole. Both are geodesic, so both are locally maximum length curves, but they are not the same. So saying that we go along a geodesic is not a unique statement. There may be several geodesics. And this already poses some difficulties if we want to think of time as something that is path independent. Because of course I said the time that passes from here to here depends on the path. But you may now say, okay, but let's just define that the time difference between P and Q should be the time difference that a clock measures that moves along a geodesic. Now, when a geodesic, as I said, a geodesic is not a uniquely defined object in general. It is certainly in flat space-time. Okay, so let's say you have a meter stick. And of course, we have a very intuitive feeling that we know a meter stick is a very well-defined object. It has actually the length of 1 meter. So let's suppose this is a meter stick or a length measuring stick. Now, what does that mean to even say that this is a meter? So if I draw the meter stick in space-time, it's actually an extended object. So the meter stick consists of 2 ends, and each end of that meter stick is described by a world line. So let me draw the meter stick here just abstractly. So the meter stick has this end, I call one end A and the other B. And so we would have 2 world lines, gamma A and gamma B. Now you see already the difficulty. What does it mean in this diagram here to say that the meter stick is really 1 meter long? That's problematic because, as I said, we can only measure distances a priori between events. But there's now not a uniquely defined event here and here. So what does it mean to measure the distance between A and B? We somehow have to measure the distance between these 2 curves. That's challenging. Now, what we usually do, and what you probably are used to in case you did special relativity, is to go to Minkowski charts. I mean, that's, as I explained last time, the type of chart we always use in special relativity. So we go to a chart, and in this chart, we choose it in such a way that if the meter stick is, for example, at rest, or if you go into the rest frame of the meter stick, then the A point is just a vertical upwards, and the B point as well. So the chart representations X of gamma A and X of gamma B are just straight, now really in the diagram, straight vertical lines. Now still, what does it mean to measure the distance between the 2? Now it's much more natural. We would say, okay, the distance between the 2, if this is here the length scale, this is position. That would be, of course, three-dimensional, but still this is position. We just could say, oh, we look at this coordinate. So here we have the coordinate value, let's say 0, and here the coordinate value 1. So we could say a meter stick is defined as an object which has the property that if I go into Minkowski coordinates and choose the particular Minkowski coordinates in which the meter stick is at rest, so I go into this particular picture, then a meter means that in these coordinates here, I have just a distance of 1 in whatever units I used. But of course, I said last time we are introducing the units of time as the fundamental unit, because that's how we essentially map out space-time. But now we somehow have coordinates and we go in this direction and say that's 1. Now there are lots of choices that went into that. And I want to maybe try to explain to you that if you do that in the most general case, there are various assumptions that make this whole definition of a length, of a spatial length, quite unnatural. So the first thing that we introduced in doing this process that we do in special relativity is, first of all, that we implicitly, or sometimes this is made explicit, of course, in special relativity, we introduce a notion of simultaneity. So simultaneity means that we said there is a time, the time of this event here at the 0 point of the coordinate system, this green point I plot here, is the same as the time here. But that's not an absolute statement. That's obviously a coordinate-dependent statement. So the coordinate-dependent statement is that I say I associate to all things on this green line the same time. And then, of course, here as well, these are all things that have the same time. So I introduce this notion of simultaneity by introducing a coordinate system. And I stressed so much that choosing a coordinate system is obviously not a physics choice, it's a choice that we do out of convenience. So when we take this, when we are in this special case of flat space-time and we have Minkowski coordinates, this may still, you may kind of have a guidance by what I said. You, for example, go into Minkowski coordinates where the meter stick is at rest, but this may not exist in general. So if this whole space-time here is curved, then it could be that you can find a coordinate system in which this thing here is at rest, and maybe you can even find one where this is at rest and the end is at rest. So both ends of the meter stick are at rest, but the metric could be such that it's not, it doesn't have this nice form eta ij that we took as a defining criterion for the Minkowski metric. Or conversely, if you go to coordinates to locally, let's say, normal coordinates, then it could be that you don't find coordinates where both things are correspond to straight lines going upwards. So it may, in other words, physically speaking, it may simply be the case that the two ends of the meter stick cannot be put into the same coordinate system in a way such that the whole thing looks like this for a metric that is kind of nice and gives you, tells you that, for example, the x coordinate just corresponds to the length. So what can we still do? Of course, we should go back to our, we should always go back to the question, what do we actually measure a priori? And the meter stick is already kind of a complicated object. It consists of many atoms, and if it's extended in space-time and space-time is curved, then we would have to ask the question, how does now space-time act on this meter stick to even understand what this meter stick does? So it's actually much simpler to go back to the notion of just measuring time and try from that viewpoint to understand what a meter stick is. So the first thing we have to notice there or recall is the following. Namely that there is this so-called polarization identity. And I introduced that, I think, rather at the beginning of this whole course. namely to make the point that if you want to evaluate a metric or we want to define a metric, but we have only an experiment that gives us the metric in the case where both arguments are the same, then we can still do that. And the formula, let me write it down, was something like this, that so if we want to know the value of the metric for vectors v and w, it's sufficient to evaluate the metric for the case where both arguments are v plus w, and for the case where both arguments are v minus w. But now we can even be more specific. We could make a choice. We could choose v as a long time-like vector and choose w as a short arbitrary vector. And by long and short, what I mean by that, it should just be such that if v is time-like, so if v is really, if you think, for example, in Minkowski space and v is pointing upwards in this time direction, then if you add a small vector in another direction, so this w, then it will still be a time-like vector. So in other words, I just require, or this long and short should be such that v plus w as well as v minus w are still time-like. But this means that for this choice, so as long as I just consider vectors of this type, I can evaluate this G using the metric for vectors which are time-like. And for time-like vectors, we know how to measure lengths. We just move along a path in the direction of that vector and measure the time that passes. That's exactly what it means to determine this quantity by an experiment. So in other words, under this condition that v is long and time-like and w short, we can just with a clock completely determine this measure here. Now, just by linearity, once you know, I mean, I will now not do that in detail, but I think you can imagine now you have this G defined for an V that is time-like and for a W that is not. You can now, by linearity, easily extend it to any vectors. For example, the fact that it's long or short doesn't matter because this whole thing is linear. I mean, that's what we put in as an assumption that the metric is linear. But by linearity, we can now change the length. And now by linearity, adding vectors of different types, we get this measure for arbitrary vectors. So in other words, the point here is that if I only have a clock, I can still determine this measure G for vectors that are arbitrary, including space-like vectors or also light-like vectors, of course. So what that means physically is the following. So let's suppose we have now two events. So I said we can only measure distances between events, but let's suppose the distance between them. So I have a notion of simultaneity introduced. Let's say this here. So I already said this is the first artificial choice, but let's suppose we have somehow done this. I've introduced a notion of simultaneity, and now I want to know what's the distance between these two points, which are now still events, but now it makes sense to talk about the spatial distance because I've defined that they are simultaneous. So the procedure I described above would really mean in practice that I somehow put a clock here or several clocks and let the clocks evolve along different paths. These are now, so the orange lines are now lines that should be time-like. So these are possible world lines. And then I just compare I just read off the values of the clocks here and here. And maybe I need to do that with more clocks than only 4 in this case. Maybe I need to do it with many. But if I have sufficient data, I can essentially, like in the procedure I described here formally, infer what the distance is in terms of a vector of this thing here. So by distance, I would now mean like you move along a vector or along a curve in this direction that is straight from here to here. And so In other words, the length, this blue length is a derived quantity. What you measure is the orange thing. You measure that with clocks, and then you go through this procedure and you determine the blue thing. So in other words, in this approach, the length is never measured directly. But actually, if you think about what you do in practice, if you measure distance, if you want to, let's suppose I wouldn't know the distance between Zurich and Basel, let's say. So one thing I could do is I could go with my car to Zurich or my bike and start there, put a kilometer counter there and just then start to cycle to Bern. And then, of course, in Bern, I get an outcome. But actually, I now measured somehow an event between when I started in Zurich, which was much earlier because I'm not that fast, and when I arrived in Bern. So I actually measured events that are not simultaneous. But somehow by making additional considerations like that Bern was relative to the Earth at the same place as before, and that my kilometer counter was relative to that same Earth and so on. So I make many put in a lot of stuff that I know about how the world is put together, like that streets are fixed and so on, which is all trivial things, but I put that all in and then I conclude, the distance between Bern and Zurich is whatever, 80 kilometers or 100 kilometers. And this is a bit the same here. So here we do a rather indirect experiment to determine this blue thing. So with that, I just want to explain that a notion that is very, let's say, usual to us, the notion of distance, is from the viewpoint of GR, if you really start with, let's say, in an axiomatic manner and say, let's suppose a priori we only measure time, is a highly involved concept, the distance, the spatial distance, something that depends on many choices you made. Now, it could even be that it's actually impossible to make these choices. So let me, and that's the last remark about this whole topic. So let's again take a manifold here. And as I said, we first of all need to determine or to specify a notion of simultaneity. Now, what does, again, this blue thing should be the ends of my meter stick. So what could simultaneity mean? So how do I, in other words, put these green lines that I put in this diagram here, just by saying, let's go to a Minkowski diagram. How do I do that in general if I don't have a Minkowski diagram? So because the space-time may be curved. So one thing I could do again operationally, but this is just the definition at the end, is to say, okay, I want to see when are two events, one here and one here on this line simultaneous. One experiment could be to take here at the orange point a light source, shine with this light onto a mirror that is on the blue, at the other end of the meter stick, and then reflect the light and measure here when it arrived. And now I could say, by definition, of course I have clocks here, so I have a clock running from here up, and I just half in the middle, according to time, this is now the middle between two times I measure, I say this must have been, this point should be by definition simultaneous to the point where it was reflected. So that gives me a notion of simultaneity, and that's probably the usual notion of simultaneity that we are actually using in daily life, and also actually the notion of simultaneity we're using when we are really determining lengths today, because today even the very definition of length is of course via such an experiment of this type. You shine light from one end to another end and let it reflect and measure the time it passed. So, but again, the point here is that we made a choice. We made a choice to say that I do this particular experiment, shining light from here to here to determine simultaneity. Now, if I did the experiment from the other end of the meter stick, it's not clear that I would end up with the same notion of simultaneity. Actually, I will not in general. In flat space-time, I would, and that's the reason why in flat space-time it still makes sense to talk about meter sticks, but in a curved space-time, I simply wouldn't. So if I do the same experiment here, let's do it. So I start here and I have this light here reflected at some point and it comes back. So it could still be that they arrange it in such a way that the middle time between the between the two red dots is here, coinciding with the green dot of the other, but now the reflection point is a different one. So the new notion of simultaneity of this definition would be this green line, which is a different green line than the dark green line. So the two ends of the meter stick would kind of result in two different notions of simultaneity. And correspondingly, of course, now a statement about how long the meter stick is, which, as I explained before, is at the end a statement about two events, is now either a statement between this event here or this event, or between this event and this event. And these are just the different events. So clearly we shouldn't expect that we even get the same result. So the length of the meter stick is just not well defined. So this is all things you should keep in mind. Of course, I mean, you know, when we are in a sufficiently small region and so on, then we can neglect curvature and everything works as we are used to it. But if you are starting to think of an astronomical size meter stick, then it simply doesn't work. Its length, you would just have difficulty even defining its length, even constructing it in a way. Of course, you could say, okay, you just construct it by putting many known meter sticks next to each other, and you know each one is a meter. So if you put 1 million of them, you have 1 million meters. But of course, if space-time is curved, there will be some action of this curved space-time of the meter stick, so it may be contracted, and so it depends at the end on the material of how it actually behaves and what length it measures. Okay, so the bottom line is it's not a good idea to directly measure distances using meter sticks in GR. Okay, so I think that was now my longer comment about this question, but I think that was a useful thing to anyway mention, because that's an obvious question that should come up anyway, because you should try to connect the things we learn to your daily life intuitions and start to understand which things from your daily life intuition are still valid in this general context and which other concepts that you're very used to and familiar to, you should better forget not to get confused. And the notion of a meter stick in this direct way is maybe something you should at least use with care in the spirit of what I explained before. Maybe the whole thing will even again become actually or pop up in the next section, which are Rindler coordinates. Okay, now I make a jump, but let me just briefly motivate what we're going to do. So we are now going back to flat space-time. This would actually be the topic of special relativity, but we are now looking at flat space-time in coordinates which don't transform linearly to each other. And I said last time that what is special about special relativity is the physical thing that we are considering flat space-time, as well as the kind of convenience or artificial choice we make that we only consider linear transformations between coordinate frames. You only are looking at inertial coordinate systems usually. And Rindler coordinates are connected to an accelerated coordinate system. And that's what we want to study. So maybe just to give you a hint on how we are going to use that. So why are we interested in accelerated coordinate systems? The reason, I mean, the simple reason is in a way, if you now put up a coordinate system where you sit or stand right now, then you would probably end up with a Rindler coordinate system. And the reason is simply that you are constantly accelerated. You're accelerated towards, I mean, you're actually accelerated away from the center of the Earth. The floor or your chair or wherever you sit accelerates you upwards with the usual acceleration g, 10 meters per second, constantly. So you're constantly accelerated. And this is the picture you should really have in the GR context. In the GR context, the free-falling movement, and I hope you're now not free-falling, but the free-falling movement would correspond to the geodesic, to the straight line in space-time. So now you're not describing, as you're sitting, you are not describing a straight line or a geodesic in space-time. You're actually on a curved world line. But nevertheless, of course, you want to have coordinates that keep following you as you are accelerated in space-time. And these are the Rindler coordinates. Okay, actually I forgot to ask whether there are questions about the other topic, because that's a topic that may indeed raise many questions, this whole discussion of measuring lengths and times. Okay, if there are no questions about that, of course, feel free to interrupt later, but then I will continue. So as I said, we are in flat space-time now, or back in flat space-time. So in particular, as we have seen last time, we have a nice coordinate system, namely the Minkowski coordinates. And I will, for the moment, indicate the coordinates with respect to the Minkowski system, to the Minkowski coordinate system, as capital T and capital X and so on. So the Minkowski coordinates, this is just a choice, are now denoted like this. Of course, in the diagrams, I will from now on always restrict, as usual, to 2 dimensions, and to in this particular case only to the X coordinate, and omit the others. Now we will also have so-called Rindler coordinates. This is, of course, the title of this whole section. These are just different coordinates. And these coordinates I indicate the first component by omega, the second by r, the third by y, and the last one by z. So you see a kind of asymmetry between how I treat x and how I treat y and z. And the reason for this asymmetry is that, as I just said, Rindler coordinates capture an accelerated reference frame, and the acceleration will be in the x direction. So in a way, not much happens with the y and z directions. That's why we can also easily not draw them. Now the Rindler coordinates will look as follows. So I just draw the coordinate lines. So let me draw the coordinate line of the coordinate, for example, when I let r be 1, and I vary omega. And the others that I don't draw, you can just, so let's for simplicity just assume y and z, both capital and non-capital, are set to 0. So this will be the coordinate line r equal 1. Then I may have a coordinate line r equal 2, and one r equal 3, and so on. Now, actually, r is always positive. R equals 0 is not considered. Then we have coordinate lines for w. So the coordinate line w equals 0 just corresponds to this horizontal axis. The coordinate line w equal 1 corresponds to a straight line with a small slope, then w2 with a larger slope, and so on. And then the things will get more and more narrow until we get a slope of 45 degrees, and there are no coordinates above that. So the Rindler coordinates will actually only cover this region, or this region here. It also goes into the negative direction, but it will essentially only cover a part of Minkowski space. So there is simply no Rindler coordinate associated to a point here, to this point, for example. It doesn't have Rindler coordinates, only those that lie here. And of course that means I have made a choice. So this origin of the Rindler coordinates determines which regions I will actually cover. Now okay, that was just a graphical thing. So what are these lines more formally speaking? Let me write this here. So I hope you're familiar with trigonometry and hyperbolic trigonometry. I'm sure you are. And with them, I can easily express the transformation rules. So remember, to give a coordinate system, what I need to do is I always need to give a chart transition map. That was what we did for manifolds. And the chart transmission map, now to go from Minkowski coordinates to Rindler coordinates, I will express in the opposite direction. Namely, if I have a Rindler coordinate, I have a little r. How do I determine, and a little omega, how do I determine t? So it's given by this formula. For the x, it's r times cosinus hyperbolicus of omega. We'll just call this cos h. And as I said, I will assume here that you know these functions. Otherwise, please read them up and read about their properties of these trigonometric functions. Now, why does this correspond to the above? So you see, if I let r be fixed and vary omega, then of course this gives these orange curves. So these orange curves really correspond to the behavior of these functions. And I will just maybe give some more intuition why. But what you can already see immediately is that if you fix omega, then of course the fraction between, or the ratio between t and x is now fixed. It's just sine h over cos h. And so if I vary r, I just move along such a line. And this fraction between sine h and cos h can never be larger than 1. That's just a property of these trigonometric functions. And therefore, we cannot have here a line with a slope larger than 45 degrees. Okay, maybe I just make some notes that are useful to understand these coordinates. There will also be an exercise about them. So it's useful to familiarize yourself with these coordinates. So first of all, I can just calculate this. Okay, I just calculate x squared minus t squared. And I will explain afterwards why I do that. So what's that? That's cos h omega squared minus sine h omega, the whole thing squared. Now, one of the properties of these hyperbolic trigonometric functions is that this always gives 1. So that's actually the main difference to the normal trigonometric function, that there is a minus sign here. But if you put the minus sign here, then this gives always 1. So this is just r squared. So you see, and that now explains these orange lines. If I fix r in this formula, then this means x squared minus t squares should just be equal to a constant. But x squared minus t squares is just a hyperbola. And these are these orange hyperbolas, which of course continue also in the negative direction. So that essentially explains the diagram that I've drawn. Maybe just for completeness, let me also write down this ratio between x and t that I mentioned before. Or let's do it between t and x. So the ratio between t and x is, of course, as I said before, sine h omega divided by cos h omega. And that's, by the way, by definition, tangent hyperbolicus of omega. So tan h of omega. So from these notes, we can also see the inverse transformation. So of course it follows immediately from what I just wrote that omega is therefore the arcus tang h of t over x. And r, the small r, has to be the square root of x squared minus t squared. So we now have the inverse transformations. Okay, I just wrote them down. I mean, that's all very trivial algebra, but I wrote them down because we will make heavy use of them later. Let me also remind you that, of course, the metric of Minkowski space, and the metric is the central object defining the geometry, is this one here. And okay, there are also, let me just put that in gray, the other terms which I will in the following often just not write because we are, I mean, not because they're unimportant, but because they're kind of, their behavior will be trivial. They'll just remain there. And we will make coordinate transformations where the other terms change. Maybe I forgot to say here, and I should have said that in these, oh no, actually it's obvious. Of course, the inverse transformation of y here is also the identity. So really on this side of the metric, if you now go to another metric, or if you express this metric in the Rindler coordinates, this gray part will just be a little y and a little z. Nothing changes otherwise. Okay. Now let us study this metric a bit more. And one thing that is useful is to understand the tangent vectors of these coordinate lines. So what are the tangent vectors? There's, for example, a tangent vector if I keep r fixed and vary omega. So that should be a vector pointing like this. That's what we would expect in this particular case. But we need its expression formally. So let us write down this expression. So what I mean by the tangent vector along the coordinates is, of course, d to the d omega. Now we express it in the coordinates of the original Minkowski we want to express it in the Minkowski coordinates. So we do a coordinate transformation, and the coordinate transformation in this particular case looks like this, as you can easily verify. You should now be familiar with coordinate transformations. These are the only relevant terms because t only depends on omega and excuse me, omega only depends on t and x and not on y, so the y's are always unimportant. And now I can just calculate that. So I just take the derivative of t with respect to w and so on. So, I mean, we have these expressions here. And of course, these derivatives are very easy to take. You should just know that sine h, the derivative of sine h is cos h, and the derivative of cos h is sine h. There's no minus sign. That's another difference compared to the trigonometric functions that you know otherwise. So what we get is just this. So I take this derivative, the r remains, and I have this expression here, d to the dx. So that makes sense, because if you look at this vector, I mean, what is it? I mean, this is a vector. I mean, if you just read this line, it's a vector which points by this component, cos h, into the t direction, into the vertical direction, and by r sine h into the horizontal direction. Now, cos h and sine h, I mean, this is just essentially the, yeah, I mean, it's again proportional to this, just with sine h and cos h interchanged. And if you look at what that means in the diagram, then it's indeed a vector in this direction that I indicated before. So it will be a vector here in this direction. That's what this means. And that's it. You can verify by just evaluating these hyperbolic functions. Now, one thing that we will need, and let me still do that before the break, just as a remark, is that we do it in another color here. The length of this vector with regards to the metric is, of course, just r. I mean, the length, okay, the length squared is r squared. So how can I see that? I just evaluate. I mean, I need to put that into the metric, but of course the metric was given in terms of d to the dt and d to the dx, where it's just a normal Minkowski metric. So I have to square this and then subtract the square of this. So I get r squared cos h squared minus r squared sine h squared. But I told you already before that these two cancel to 1. So I just get r squared. So the length of this vector is r squared. And we can do the same game with d to the dr. That's just the direction vector if I increase the r component. And here I again take the derivative. I'm not doing that in the same level of detail. I just write down the solution. But you can, of course, see immediately that if you take the derivatives, in this case, we need to take the derivatives with respect to r of these expressions, we just keep sine h and cos h. So we have this factor here and this factor here with the corresponding basis vectors d to the dt and d to the dx. And let me also calculate the length of that. So what we get here, in other words, the length squared. If I write g, this is now just -1, because this squared minus this squared gives -1. And just for completeness, the last thing before the break, d to the dy is of course the same as d to the dy large, and d the same for z. That may also be useful later. So now we did a lot of preparation, and after the break, I will tell you even more about this metric, and we will see how it is useful. And what we will see, this metric will give us an interesting insight, and you may want to think about this already now in the break. It's connected to the following experiment. Let's suppose that there was a light beam somewhere sent out in some remote place. Let's say somewhere in Spain, someone emits a light beam. Now you could ask yourself, is it possible for you? So let's suppose this light beam comes towards you, and you have now the choice to run away. Is it possible for you to escape the light beam? Now the seemingly obvious answer is no, because you cannot run faster than light, I guess. And the light beam, of course, has velocity, is equal to moves with the velocity of light. It's a light beam, so it will hit you. However, what you will see is that if you accelerate strong enough, it will still be a bit unrealistic, but in principle, if you accelerate strong enough, you will be able to escape the light beam forever with a constant acceleration. So you just accelerate sufficiently hard, keep accelerating all the time, and the light beam will never hit you. That's something we will actually get out of these calculations. So despite the fact that these calculations are rather, let's say, algebraically simple, they will give us some interesting insights. And this same insight will then be useful later to understand black holes. In some way, the black hole horizon will just be like the light beam that comes after us and we accelerate away from it. Okay, but let's first make a break until 1 o'clock. Are there questions that you would like to answer during the break? Jan,
just a short question about this metric. So what are the cross terms, like g of the
yes,
you know, when you have one
yes.
in one direction, one in the other.
Yes, now I just gave
are they orthogonal or
the metric for the non-cross terms. Yes, so you can easily see from what I just calculated that, for example, d to the dr to d to the d omega. That's actually a good question because we will need that anyway, but I will mention it again. This is actually 0. And the way to see that is simply to essentially, we have these two vectors, d to the omega and t to the r. So you can again insert it into the metric. And if you insert it into the metric, you will see you get a component. So first of all, you get a component this here multiplied with this with a weight of +1. So you get r times sine h times cos h. And then you have another component of the metric. The metric is diagonal, the Minkowski one. So you now only have this term times this term. But this second part, this is now the negative part of the metric. You see, this is now, where did we write down our metric? Not sure. Here, so this is now this part. This comes in with a negative sign, but we have again r times sine h times cos h. So the two terms just cancel so that we get a cross term of 0. Does this answer your question?
Yes, thanks.
Okay. Thanks for the question. Are there other questions? Or was there anything in the chat that I should answer?
No, there is nothing else in the chat.
Okay. course, feel free to also ask questions that came up in the last lectures, because I didn't have much time to answer during those lectures at the end of the lectures or during the breaks. I think we had almost no breaks last week. I could also go back to this material if you like.
I have a question.
Yes, please.
In the discussion of the length and in the beginning of the lecture, where can we see that the length contraction?
So you're referring to today's lecture?
Yes.
Yes. Okay. So yes, so here we don't directly see that. I just essentially refer to the last lecture, but maybe I could relate it again to the last one. So if you look at, I mean, I drew now a very complicated orange path, and in particular a green path that is quite involved, but let's say a simplified one would be the one that we have seen in the context of the twin paradox. So that would just be a very similar picture, but if I drew the twin paradox, then I would really have one observer, let's say, that stays on Earth, and one that moves away, it comes back. Now, of course, from this diagram here, if I just gave you this drawing, even if I made the drawing very precise, you would not be able to see at all. There would just be not enough information to determine which of these two observers now experiences a shorter time. The only thing that you can say is that in general, you know that the length of a curve determines the time, and quite obviously, different curves don't have the same length. So that's clear. So this diagram a priori only tells you you should expect that different people who make different trajectories will end up with a different time on their clock when they compare them here at point Q, even if they started at the same time. Now, to really see that there is a time dilation, we need to evaluate the length of the curve explicitly. And for that, we need to also be more specific about what is the geometry of this manifold and what is the actual curve. And that's what we did in the case of the twin paradox, where we said, let's now go into the special case where the manifold is essentially flat. And then we can go into Minkowski coordinates. And then in the Minkowski coordinates, maybe I'll go briefly to them, back to that. In the Minkowski coordinates, the situation now looks like this. And then we could calculate. So remember, we then did a calculation where we said, let's now just insert all the stuff. We know the metric. The metric is now the Minkowski metric. We have a description of the actual curve. And the curve, you see here, the curve entered. These were the direction components of the curve. And then we got, as a result, that while the green curve has length 1, the orange curve has a length that is a bit shorter, depending on how fast here one moves away. Now, the insight here that I generalized was kind of that if you now are in this Minkowski example, this observer here, the green curve corresponds to a straight line. So in Minkowski coordinates, straight lines in the coordinates are really straight lines in the manifold sense. And we also, therefore, you could now do the same calculation for more curves, and you would actually easily be able to convince yourself that whatever curve you take, not necessarily this orange one, if you start at the point here and if you end at the point here, you will always experience a bit less time than 1. And that's actually what we even showed more generally. We said that the geodesic is a straight line, and the geodesic is at the same time defined by being the extremal curve. Now, what is not completely obvious a priori is whether extremal means the shortest or longest. But because we have now seen that in this particular example, at least the curve gets shorter in terms of its length. It looks longer, but it's its actual value in terms of the metric is shorter, we know that extremal means, at least in this locally flat picture, that it's the longest curve, or physically the longest time. And that's essentially what I now kind of express in a more general way. So the orange curve should express the geodesic, and the green one should express one that deviates from the geodesic. And the intuition from the twin paradox was that the larger the velocity is, the relative velocity of the green curve with respect to the orange that is a geodesic, the larger is the time dilation. So that's why I drew a curve like this. So this should indicate someone who moves around a lot. Maybe he circles around the other observer. I mean, someone who would circle around the Earth very, very fast would actually experience much less time. So that was the idea of this. I'm not sure it answers your question, but that was essentially what I tried to express here at the beginning.
Well, here we can see that the time dilation, right? So one of them is actually longer than the other one. But in the special relativity, there is also another concept of this length contraction.
Yes. Mm-hmm.
Right. And can we see the length contraction in our setups somehow?
Yes. I mean, first I should say, just to be clear, that, I mean, when we say we see the length, we see the time dilation, I mean, the diagrams are of course misleading, because the orange curve looks shorter but has a longer time. So we only see it if you do the calculation and take into account the metric. Now for the length, I think there are really too many choices. So in a general curved space-time, there is simply no well-defined notion of length. That was essentially my point. You need to make many choices before you can even say what do we mean by the length of an object in general space-time. Of course, if you again are in a very small region that is flat or approximately flat, then you can do the very same considerations that you do in special relativity, and you have the very same type of length contraction as you are used to if you know that already from special relativity. But my point is that if you now go into a region where the curvature matters, where it really matters that you're no longer in flat space-time, then the curve, or then the notion of length is a highly artificial one, because it depends, for example, on the notion of simultaneity. And the simultaneity for a meter stick that is kind of in flat space-time can be well defined, because I just say it's a simultaneity with respect to the reference frame, to the Minkowski frame in which the meter stick is at rest. But if now the meter stick has two ends that somehow are so far apart that the curvature matters, I don't find a Minkowski coordinate system again to even say that. So the bottom line is the length contraction is still the same as in special relativity if you look very locally. You just look at very small lengths and so on, but and then it's approximately the same, because then you can kind of come up with a reasonable definition of lengths, but not in a general manifold. Does this answer your question?
Yes, it does. Thank you very much.
Okay, you're welcome. Okay, I think it's time to continue. I'm of course still happy to take questions if there was something that is still pending. Otherwise, let me continue with this discussion of the Minkowski metric. So just for those who were not present during the break, there was one question which resulted in me writing down something I should anyway have written down, which was, what about the cross term? So before the break, I evaluated this thing and this, and how I said, we can also evaluate this cross term, and it's done in the very same way. We just insert these vectors that we have explicitly into the metric, and then the evaluating that shows that you get a term this times this, and you get another term this times this with a minus sign, because you're in Minkowski metric, the two cancel and you get a 0. So the bottom line is there are no cross terms. As I said before, I will not write down the y and z term. They're just trivial. They're always of that form. But I could just summarize the metric, or what I found about the metric here. So I can now express the metric in these new Rindler coordinates. Namely, I now know that I have this. So what does this mean? This is the essentially 0, 0 component of the metric. So the 0, 0 component of the metric is therefore r squared. And the 0, 0 component is now, of course, the omega component. So just rewriting what we have essentially found in a different way means that we have the metric being of this form in the first component, and in the r component it's of that form, so we just have a -1. So we get, and we have no cross terms, of course. So we have here dr tends to dr, and then let me for the last time again write the grazing it. We would still have dy and dz. Okay, so in other words, in this metric, in the Rindler metric, we have this additional factor here. And so you see double, or omega, this should be an omega. The omega component, so the omega is something like a time. It has a positive prefactor, but it's like a scaled time. But the scaling depends on how far you are away from the 0 point. And that's kind of interesting. So that makes these coordinates interesting. That a priori doesn't tell you much. I just wanted to make you aware of that omega is still something like a time, whereas r is more something like a distance. And I mean, more formally speaking, the vector dr is indeed a space-like vector, and this is a time-like vector. So in that sense, is this component a kind of measure for time in these coordinates. Okay, I think it's now a good idea to essentially look at, something you should always do when you have a space-time given by a metric, and even if it's flat space-time, you should look at trajectories of objects in this space-time. And there will actually be an exercise today about another metric, the Schwarzschild metric. This is the metric we are in now if we model Earth as a gravitating object, which of course it is. So the metric that accurately describes the space-time we now experience here is actually the Schwarzschild metric. And there will be some calculations there of moving objects and so on. And only once you understand the trajectories of objects in a metric, you really understand its geometry or its physical meaning, because the geometry itself, as I said last time, is essentially irrelevant if you don't know how the geometry couples to matter. So a statement about the geometry alone is not a physics statement. But once you say, in the geometry you have straight lines and that's how matter behaves in this geometry, that's then a physics statement. And so, in other words, to physically understand the geometry or a metric, the geometry is given by a metric, you need to look at, for example, free-falling particles in this geometry and then study how they behave and so on. And that's what we are usually doing. So they don't necessarily need to be free-falling. So what we do here is actually we look at curves of people who move along coordinate lines. So we suppose we have observers who are moving along these orange lines. Of course, there's an observer here at r = 1, one at r = 2, at r = 3, and so on. Now, obviously, if you look at this world line, it looks as if, not only looks as if, it's because this is flat space-time and we are the overall diagram is Minkowski, this is an accelerated curve. So an observer describing this world line is constantly accelerated. That's what I said before. We are introducing Rindler coordinates to essentially model us being constantly accelerated by the ground, by our chairs and so on, or wherever we stand or sit, away from the center of the Earth. And so these orange lines, in that sense, model us. And so r = 1 could be someone on Earth, r = 2 could be someone who is twice the radius of Earth away from it, and so on. So that's the way you may think of it, informally speaking. We'll make that more precise. Okay, now to do that, it's useful to actually look at the velocity vectors of these orange curves, of these trajectories of the observers. So just to have this written down explicitly, because otherwise it may be confusing. So we're not only ignoring y and z, let's even set them to 0. Of course, this actually means we can still ignore them, but this just leaves, avoids ambiguities. So there's no movement in this direction in particular. Now, as I said, we look at coordinate lines or coordinate curves for fixed r. And these are, of course, curves. So we call them gamma with a little r, because it's a whole family of curves. And each curve is a curve parameterized by a curve parameter tau, and then gamma r tau. Now I need to make sure, I mean, that's our usual convention when we use, at least when we write tau, then it's certainly the convention that if I calculate later the length of the curve, or the length of the curve of the direction vector of the curve should be 1. So therefore we parameterize the curve as follows. Now I use a notation that will be, that you may have already seen in the exercises. Instead of putting an index here, I just put the name of a variable. And of course, this variable, this is just a 0 index in terms of the Minkowski coordinates. So maybe it's important at least once to specify what I mean here. So our usual notation would be the following. If we look at a velocity vector, so let's suppose we look at, let me do that later. So this is just essentially gamma r 0 if the zeroth coordinate is t, and correspondingly later we will, or just maybe in a minute, we'll also write down this will be gamma r1. So instead of using the index number, I just put the variable, and this is useful because if you work with different coordinate systems, this is then not only an index, but at the same time it reminds us in which coordinate system we are actually working, whether it's in the Minkowski system or in the Rindler system. So let's now express the coordinate lines, these orange lines, in the Minkowski coordinates. That we can of course do, and that's just by definition essentially what, I mean, we have already defined what the curve does. That's essentially this thing here. So I just will copy that. That's essentially defining the coordinate lines if I keep r fixed and change omega, but I now reparameterize it in an appropriate way so that the direction vector will have length 1. So I'll take this and as I said, I'll modify it very slightly. I will just write as an argument now tau divided by r. And this division by r is there because it will exactly cancel with the length that you would get otherwise, as you will just see. So let's maybe calculate the direction vector. So, so the direction vector of the curve is, of course, as usual in our usual notation, v gamma. And now, again, something about notation, which I will write in blue. So what I will give the whole vector in coordinates. Now, usually we would, again, give coordinate names a number, an I, for example. And what that means is of course, that we take the i's component of the vector. So remember, that was what this dxi does. It takes out the i's component. And we also had then this abbreviation that we said we just call that gamma dot I. So this is the familiar notation that you're used to. Now we will adapt this notation a little bit, again in the spirit of before. Instead of writing the I I will just write again the name of the index. So if I'm interested in the t component, this is somehow this dt of this velocity vector, I will write this as this. So this is the same as just the one for I equals 0. And of course, similarly, the x component, so the first component, not the zeroth, the first, I will just write as that. So this blue stuff that I wrote down is just for you to be able to make the connection to this index notation now, with the notation I use now, where I replace the indices by these variable names. Of course, the rules and everything stay the same. Okay, we can now do the calculation, which we should do, which is again very simple. So what is gamma dot t? So what's the zeroth component in this sense? Of course, I just need to take the derivative of the curve. That's how the velocity is defined. So I take the derivative this with respect of this with respect to tau. And now you see that the r cancels because I get a 1 over r here, and it cancels with this prefactor r. And of course, the derivative of sine h, you know now, is cos h. So what I get is just cos h of tau over r. And similarly, the x component of the curve at r, so this should be an r here, the little index, that's where the curve is. It's the curve that goes through where r is fixed. This component is just sine h tau over r. And so I could now again write this vector, if you like, at a point tau in terms of the Minkowski coordinates. So this would be cos. I would just copy the components I've calculated. So the first component is this, but if I write it in as an expansion of the basis, I get this expression. So this is now something you should be very familiar with, these type of calculations. But now I can compare this expression with the expression we already calculated for d to the d omega. And you see it's just the same up to a factor of r. So if you look at here on the right-hand side, this thing, then you immediately realize that you can write this as 1 over r d to the d omega. Of course, everything should be evaluated at the point gamma r t. That's also true above, but I write it down here explicitly. Now you see that indeed this velocity has length 1. That's now obvious because you already know this vector here has length r. That's what is written here, and the prefactor here cancels out. I mean, it's also already clear from this. Now, the next thing I want to consider is the acceleration of the curve. Now, we haven't talked much about acceleration so far. Acceleration is a concept you probably know well from classical mechanics, but in the context of GR, we haven't studied it. However, we have studied velocities. I mean, last time we went quite deep into the relation between 3 velocities, which are the velocities we usually describe in our daily life, and the 4 velocities, which are the much more natural concept in the context of GR. And for the acceleration, we can do something similar. We can also consider an acceleration that is natural to GR, and this should be a 4 vector. So what would be first of all, just a very convenient or obvious way to define the acceleration? So you know already that an object that is not accelerated is a freely falling one. And we already gave a condition for what freely falling means in our mathematical framework, namely it should be a straight line or a geodesic. But that means formally that the covariant derivative of the velocity of this direction vector of the 4, I mean, this is kind of not the 3 velocity, of course, that's really the direction vector of the world line. Its components are the 4 velocity. This is 0. So that means no acceleration. So,
sorry, could you scroll
yes.
right a bit, please?
Pardon?
Could you please scroll to right?
Yes, sure, yes. Okay, so what the expression that I wrote down means no accelerations. Now it's natural to say that, okay, in this case, if this is not zero, that should mean acceleration. So it's natural to define a vector. Let me call it here A. Not sure this is a standard notation in GR, but just for the moment, let me call it A. And we could now say this should be our kind of, it's still a vector really in space-time. So it's in a way the 4 acceleration. I mean, 4, of course, because if you look at the components, you will indeed have 4 components. So, okay, that's now just a mathematical definition, and it's unclear whether this has anything to do with the acceleration that we mean when we talk about accelerating in a car or whatever. So, but let us first of all see whether it at least mathematically and generally physically makes sense before we connect it to our intuition. So mathematically, we of course know that the covariant derivative of a vector is again a vector. And this is important because a vector is an object that is defined independently of the choice of coordinates. And I told you many times that the physically relevant things should have a life independent of coordinates. So if there's really something, I mean, an acceleration should be something that is independent of coordinates, because if I'm in a car that accelerates, I really feel that. I don't need to first define a coordinate system to feel the acceleration. Or if you go through a curve skiing or so, then you feel that acceleration very hard. And so something you feel must be something physical. It cannot be a coordinate dependent choice. So obviously we would expect that the acceleration is something that is in this context, in this framework of GR, a vector, and not just some coordinate dependence. So that's certainly fulfilled if I define it in that way. So that's one criterion, but let's now see whether it indeed corresponds to what we would consider acceleration in our normal 3-space picture. And to do that, that's now independent of Rindler coordinates. So maybe I just put it in another color to make this. This is just a little box as a remark about acceleration. So let us consider a situation where the 3 velocity of an object is small. So we look at an object and we want to understand its acceleration. Okay, actually, I still need a diagram, so it's maybe not a good idea if everything is orange. So let me put here a little sketch. So let's suppose we go to normal coordinates. Locally, I mean, when I told you the procedure to understand whether something makes sense in our daily life intuition is to go, first of all, to locally normal coordinates, or normal coordinates at the point where we are, because these are the coordinates which correspond to the kind of freely falling system. Now freely falling, of course, we are usually accelerated, as I just said, as we are standing here, but the physics should, at least in a freely falling system, behave as it is prescribed by the usual law. So let's go to a freely falling system, meaning a normal coordinate system. And now we have a trajectory here of a particle. Let's suppose this is now a particle trajectory. And let's assume that it has a certain, of course it has a certain direction, but let's assume that this velocity, this 3 velocity is quite small. Now remember, the 3 velocity is kind of the ratio between the spatial components. So it's somehow the spatial direction of this vector relative to this time component. And so if I have a vector that is pointing almost perfectly upwards or very much upwards, then this corresponds to V being small. Of course, V is a coordinate dependent choice. So I choose a coordinate system in which the object moves slowly. And slowly means always compared to the speed of light. I mean, it means that because V in our framework is essentially a dimensionless quantity. But if you would introduce dimensions, then it would be, of course, be the usual, whatever dimension you use for velocities. And then as a dimensionless quantity, the velocity of light is equal to 1 or corresponds to the value 1. So it means v has a very small numerical value in this coordinate-free way of thinking, or in this unit, in these units that we choose. So what does this mean? If it's small, now remember the formula we derived last time. We said that the 4 velocity components, and let me now only consider the first 2 components, the 0 component and the 1, and the 2 and 3 we just omit for economical reasons. So this would be given by this expression. So that's the expression we derived, where on the right hand side we have a 1 and the actual velocity, or actually more generally this was just the 1 component of the velocity. Now, by the way, there was a question last time about why I put the index here for the velocity down. And you see, this is not a vector in our differential geometric picture. So that's just a component. And somehow to emphasize that, I don't apply there the convention of our indices. So these are, V1 is not in other words, is not the component of a vector in our sense. Of course, you usually call this a vector, but it's not a vector in our sense. It's just in our reading, it's just a number, which via this relation is then somehow related to the components of a real vector. A real vector, a vector in our sense, and gamma dot is of course a vector in our sense. Now, if V is small, then we can approximate this by just saying this is roughly speaking just 1v1. So this prefactor is irrelevant because the lowest order terms of this prefactor are square terms. So I just omit square terms. That's what I mean by taking V to be small. Okay, now this orange box should continue because I need a bit more space to come to the conclusion. We have now therefore derived that, what this says is that gamma dot 0 is 1. That's what we wrote here. But what is gamma dot? Gamma dot is essentially the x0 component of the curve divided by the curve parameter tau. So I didn't introduce the curve parameter, but let's suppose, as usual, that this blue curve is parameterized by a parameter that we call tau, and which has the usual normalization condition that it's so that tau corresponds to the so-called eigentime, to the clock shown on, or to the time shown on a clock that follows this world line. Now, gamma dot 0 therefore corresponds, if I just informally say x0 corresponds to what we usually understand as time. So I said that when we go to these normal coordinates, the x0 direction is the one that we would experience as our time direction. That's what the clocks show in our lab. If you have a clock on our lab on the wall, then this is the x0 direction. So therefore saying that x dot 0 is 1 means that the t divided by the tau is approximately 1. And that's what I get from here. So in other words, I can essentially identify tau and t, which is just to say that as long as objects move very slowly, tau, like the eigentime, the clock shown on the moving object and the clock shown on the lab wall, which is t, are showing essentially almost the same time. Now the second expression that I get from here is that gamma dot 1 is equal to v1 in this approximation. So therefore, if I now take the second derivative, so if I now take gamma dot 1, this is d to the d tau of gamma dot 1. This is now approximately equal to d to the dt, because we t and tau is approximately equal, and gamma dot is approximately equal to v1. So we get essentially what we usually, okay, I think I don't even need to write something else. This is, of course, what we usually understand as the acceleration. At least now we, in the one component, we only looked at one component. So what I've now said is that the second derivative of gamma in these coordinates corresponds to the usual acceleration. So maybe I should call let me just put it in words, the 3 acceleration. So that's what we usually have, and it would be here the first component of that. Now we are not completely done. I need one more step. The last step is to realize the following, namely that in normal coordinates, which are the ones we chose. I mean, I said that you're analyzing the whole thing in normal coordinates to get this physics intuition. In normal coordinates, all the gamma symbols are by definition 0. So this means that if I now look at this velocity vector, so this A that we defined before, I think I call it A. So if we look at this vector, and we look at now a component of that, let's say the first component of this velocity vector, this first velocity vector indeed just corresponds to gamma dot 1. So this equality is only true in normal coordinates. Otherwise, I would have these capital gamma symbols in addition. But because this is now just gamma 1, we come to the conclusion that this is corresponding to the 3 acceleration in the direction 1. So what I've shown here is that if you have a component A1 of the 4 acceleration that we just defined as a coordinate independent object, this corresponds in, I mean, if you look, I mean, yeah, so of course this is now also a coordinate dependent thing. So what is coordinate independent is the A itself. If you take this coordinate independent vector A and evaluate one of the coordinates in normal coordinates, so if you go to a normal lab where people use the usual coordinates, then it corresponds indeed to what we so far always thought was an acceleration. So this justifies essentially this definition here. Of course, if the velocity is now large, this may no longer agree with our daily life intuition, but that's fine. I mean, we expect that in GR things are different in a certain regime. And there, the normal notion of acceleration may not even make sense any longer. But we can be confident that this object is always a useful object because it's defined independently of coordinates. So if you define something independently of coordinates, but can show that in a coordinate system where we understand it, it corresponds to what we want, then we should be completely happy. Okay, are there questions about the acceleration, about what I said now? Because that's a concept that, again, relates to something physical, something of our experience. And we are doing that not too often. I mean, a lot is working in a framework, but we need to always keep in mind that at the very end, we need to connect that framework to the actual physics. And if you want to make a statement about what we experience, then acceleration is certainly something we experience. So if you want to, for example, calculate what's the acceleration we feel as we stand on the surface of the Earth, we need to connect that to the formalism. That's what we now did in this orange box. We said that this mathematically defined object corresponds to the acceleration as we usually feel it.
There's a small question. Why gamma dot 0 is equal to dt over d tau? I guess this refers to the normal coordinates.
Yes, right. Okay, so I guess the question refers to, okay. So is the question about this equality?
I guess so, yes.
Yes. Okay. Yeah, so this just comes from the fact that I said that so in normal coordinates, in normal coordinates, the x0 direction is what we usually perceive as the time. And by the way, this is true because if I now have a clock that is at rest, it would just go upwards in this direction. and the tau of the clock, so the eigentime of that trajectory of the clock, would then just be identical to x0. Therefore, I can interpret x0 in the normal coordinates as the time that I have that the clock shows that is at rest in this system, at least momentarily. I mean, if it's only locally normal, then of course this is only true in a small region, but t corresponds to x0. So I use this, and now I additionally use the fact that what gamma dot 0 means, as I already maybe indicated before, what this really means is actually the dx0 component of the velocity vector, or of gamma, if you like, of the gamma vector. But if I now replace dx0 by, or x0 by t, then it's that thing here. So then it's, should put that differently. So, yeah. So I think I wrote this somewhere here. Yes. So I also used that gamma. It's not. I didn't write it here. So let me write it again. Gamma dot 0 is by definition d to the d tau of gamma 0. But what is gamma 0? Gamma 0 is the x0 component of gamma, of the curve gamma. And of course, everything depends on tau. So if I would do it more explicitly, there would be here an argument tau, and here as well there would be here as well some argument tau. Let me write it, gamma of tau. So see this, there's a lot in this notation. So gamma dot 0 actually means this. And now you can see if I now replace here x0 by t, then of course I get a dt over d tau. And of course, now this is again an abbreviation. So what it really means is it's d0 to the d tau evaluated, maybe I'll put this here, evaluated at the curve at this point, gamma tau. So now you can probably see the connection. So when I start here, I expand the full notation into the full notation. Now I can replace the x0 by t, and then it means this thing here. I hope this answers the question. If not, please feel free to complain. Okay. Okay, so after we now actually motivated the acceleration as a definition, or we motivated the definition of the acceleration, I should have said, we now can evaluate the acceleration for the trajectories we are interested in, which, remember, are these orange trajectories. So we want to see what is the acceleration really experienced by an observer that moves along these trajectories. And the answer is, again, very easy to get as long as we work in Minkowski coordinates, because in Minkowski coordinates, these are, of course, in particular normal coordinates. We have no gamma symbols and all that. We can just take the derivative again. So what we know is that the derivative of these things, the second derivative, will exactly correspond to the acceleration. So let me write this down. So the acceleration in the, let's say, t direction, because I'm now, as I said, working Minkowski coordinates, is just this object here, for the same reason as just said before. And that's, if I evaluate this at the point, okay, I should always, the acceleration may change over tau in general as I move along the curve. So it's still depending on tau. But this derivative I can easily evaluate. It's just sine h tau over r. Oh, there's a 1 over r, I think, that goes in front if I take this derivative. So it's 1 over r sine h tau over r. So essentially I'm looking at this thing here on the right hand side to do this. And the same for the x direction of the acceleration, which is actually maybe the one that is relevant for our thing, because we said the x direction is the one direction, and the one direction is the one we said corresponds to the one direction of the usual acceleration as we experience it. This will be 1 over r cos h tau over r. Now, if we look at the I forgot to say one thing. Actually, the one in this approximation that we are doing of small velocities, the a0 direction of the acceleration will just will also not contribute. So the length of the acceleration vector is essentially the same as a1. And the reason for that is that, of course, this gamma dot, if I take the derivative of gamma dot, then this is just 0. So maybe, okay, that was maybe not a very good explanation. Let me briefly add that to our box, because it may be useful for later. So let me just add that gamma dot 0 in this approximation we are doing is of course just 0. And that's what I get from here. So to first order essentially. And this implies that the length of this vector, of the acceleration vector, gamma. So that's the acceleration vector. Now I look at the length of it. So what's the length? The length is this g. And I need to insert it twice. It's actually the square of the length. The square of the length is of course then the square of a0 minus the square of a1. And because a0 is 0, we just get essentially a1 but with a negative sign. So we get this thing here, a1 squared. So that's something that will also be useful to us. That, to say that even the overall length of the acceleration corresponds to what we perceive in some way, what we experience. And that is related to this fact that I said before, we really feel acceleration. So acceleration should be something that already has a value independently of whether we introduce the coordinate system. And of course, if I just talk about a1 here, then I already introduced the coordinate system. But if I talk about the length of a vector, the length of a vector is something that is defined independently of a coordinate system. So the statement is that the length of the acceleration is really something that has a direct physical meaning. And that's again the acceleration we would really experience. Okay. So now let's therefore calculate the length of this vector, because we just said this is something relevant. So what's now the length of the vector? Again, the length of A. That's now easy to do. I mean, we have the coordinates in Minkowski, so it's just this squared minus this squared. And again, by the usual law that these two things squared and subtracted give 1, we just get minus 1 over r squared. So that's what we find. So in other words, the acceleration, so our conclusion is acceleration of the strength of the acceleration. Let's call it the strength. That's what we really feel, not the vector. So the strength in the sense explained before, when we really relate it to the normal 3 acceleration. So the strength of acceleration is 1 over r. I need to take the square root, of course. Because that was all squared here. Okay, so we found something interesting. And just before we conclude for today, let me discuss this a little bit. What we found is the following, namely that if you look at, okay, let's go back to this diagram that we drew at the beginning. If you look at this diagram here, then we have different observers, namely one here, one here, one here. All these observers experience different acceleration, namely 1 over r. So this observer only experiences half of the acceleration of this observer here. So why is this remarkable? Let's calculate the distance between the spatial distance between the observers. Now, this is very, very dangerous because I spent the whole first half hour of this lecture to tell you that the spatial distance is something that is not well defined. However, in Minkowski space, and if you define simultaneity well, then we can still define a notion of distance. And you see, for an observer who is moving, it's natural to take if you have, let's say, an observer and he has normal coordinates, then of course we can just say this direction here is what is spatial simultaneity. Now, because we are in flat space-time, that's essential. We assumed everything is in flat space-time. This works in the same sense as it works in special relativity. So we're now in a special case where we can, in a relatively natural way, talk about simultaneity by namely saying just in the coordinate system of the observer, it's the spatial direction. So what's the spatial direction of the observer here that moves with this velocity? This is just the r direction. Of course, also the y and z direction, but we are focusing on the r direction. So the r direction is the spatial direction of this observer, because the omega direction is kind of the time direction, as we have seen. So we have seen here that the observer moves along a time. So this d to the omega is kind of his time direction, but the metric has almost the Minkowski form. So all the other components are kind of spatial directions. Now, if we now ask ourselves what's the distance, we would really therefore measure the distance with the blue lines being the points of simultaneity. So I guess we have, okay, let's just, so if I'm asking myself for an observer who is moving along this line, once he's here, what are all the points that, according to this definition of simultaneity that I just made, are simultaneous? What happens at the same time? Then these are the points on the blue line. So when he's here, then it's different. Then it's along these blue lines. So the blue lines are essentially the notions of simultaneity. And in this case, they are symmetric. So for this observer, when he's here, he also thinks this is the point of simultaneity. So when this and this here, when one observer is here and the other here, they would agree there now. We have now a common time, essentially indicated by this omega. Now, when you measure the distance between here and here, the distance is just r. I mean, you see that from the metric. Remember, we wrote down the metric, and the r has no prefactor. So the r coordinate really directly corresponds to a metric. So now the difference in r between these observers is always the same. They're always distant by r equal 1, or this observer is distant from here by r equal 2, but he remains at this distance. But this is kind of strange if you now think of it. We have observers who start at equal distance. So you have one here, one here, one here. Let's suppose they're 1 meter apart. I mean, let's suppose this distance from here to here is 1 meter. Then the claim is that when here they're still 1 meter apart, from here to here still 1 meter, and even further up from here to here is still 1 meter. So these coordinates, these orange lines, correspond to observers who try to keep their distance. So they accelerate commonly, but they try to keep their distance. Now the point is that as they keep their distance, or in order to do that, they have to accelerate with different strengths, because we said here at the end, the strength of acceleration is 1 over r. And that means, of course, that the observer who is more to the left has to accelerate more strongly than the one on the right. So that's maybe not intuitive, but that's not about GR. That's already in special relativity. In other words, what we learned is the following. If you have a big object, like a very long stick of something, and now lying here along the x-axis, and you want to accelerate this whole stick. Now I accelerate the stick in this direction. It means that one part of the stick has to accelerate harder than the other part in order for the stick to keep its length. So if you accelerate an extended object, in order to keep it rigid, we need to make sure that the different parts of the object accelerate at the same length. But what we also see is that if you do that, the acceleration diverges. So here, of course, because it's 1 over r, if I'm here, I need to accelerate a lot. So an object cannot be infinitely long so that I can still accelerate it. So the object can at most, it has to end a little bit before this point, because here the acceleration diverges. So I simply cannot move an infinitely long object that is rigid. It would just break, because there would be parts that have to accelerate faster than, infinitely fast. But conversely, you see something interesting now when you look at this diagram. This relates to what I said before the break. If you emit here at this special point, at the point where the acceleration would diverge, which is of course far away. So if I accelerate a little bit here, like in my car, then this point, if my car was very extended, where the part of the car would need to accelerate a lot or infinitely fast, would be many light years away. Many millions of light years. But there is a point where there is an end point. And the interesting thing now, if I would emit light at this point, it would make this trajectory. And if I'm now this observer who accelerates at the constant acceleration a, this light ray will never hit me. Right? Light ray will go up here, whereas my accelerated line here is just a hyperbola, which never reaches that point. So I can live forever here, and this light will just never catch up with me. Of course, the closer I am to the light source, the harder I have to accelerate. And if I'm very close, it diverges. But if I'm starting at any finite distance from the light source, I'm able, with a constant acceleration, to escape it forever. As I said, this will be important for our discussion next week of black holes. So we have now all the instruments together to start discussing black holes. However, there will be also an element that we have to introduce, of course, which is the metric of a black hole, which is again the same metric that I mentioned before, the Schwarzschild metric. It's the same metric as the one that describes us here on Earth. So the metric is not different for a black hole. And in order to make you already a bit familiar with this metric, there will be an exercise today where you do some coordinate transformations of this metric. So the metric will be introduced. It's a Schwarzschild metric. I will also introduce it next week in the lecture. And then in order to understand that metric, we will need to look at it from different viewpoints and different coordinates. And the purpose of the exercise is to start this study of the metric. We will study this metric a lot more. So if you don't understand it after doing these calculations today or next week, don't worry. I will spend essentially the whole next week on this metric, on this Schwarzschild metric. But we will see that locally it will be, the behavior will be almost the same as the one here for Rindler coordinates, which is the reason why we introduced the Rindler coordinates. Okay, that's all for today.